Today we're going to learn the integral test. And so what we're doing right now is we're in this trend of learning a lot of different tests to deal with integral, or not to deal with integrals, to deal with series, with the convergence or divergence of series. But today we're going to use integrals. At this point in time, we're going to start learning some tests that if the series converges, the test will just tell us that the series converges and won't tell us what it converges to. If you remember what we've learned so far, we've learned when geometric series converge, we know what they converge to. And if I know that a telescoping series converges, I also know what it converges to. But now if I use the integral test, I can learn if a series converges, but I'm not going to know what it converges to. And the same idea is going to be true of the test that we're going to learn over the next couple days. The integral test is not going to be used on its own too often. We're going to do several examples in class today with it, but then after that, we're mainly going to use the integral test for something called p-series to determine whether they converge or diverge. So the integral test can get kind of burdensome, but it's not going to be usually the first thing that we try. Okay, so let me show you what the integral test says. So the integral test starts out with three conditions. So we have to start out with terms that are continuous, positive, and decreasing. And so we must check those conditions before we try and use the integral test. Okay, so if we have a function that satisfies those properties, then what we do is we look at the integral of the function that we're working with. If the integral, the improper integral, is convergent, then the corresponding series will converge as well. If the improper integral is divergent, then the corresponding series will diverge as well. So what we're going to have to do for the integral test is we're going to have to think back to last semester and we're going to have to do some improper integrals, okay? So let's jump into this first example to see how this works. So we've been given a series, and so the integral test talks about some function, f of x. So what we need to do is we need to turn the terms of our series into a function. We just replace the n's with x's. So the function that we're working with here is 1 over x ln x. Okay, before you ever try and take an integral, check the conditions of the integral test. Okay, so we have to check to see if this is continuous, if it's positive, and if it's decreasing. Okay, so let me continuous, positive, decreasing. Okay, so you can check these in whatever order you want, but you have to check them. Okay, so let's think about why is this function continuous? So this function is has a denominator in it. So the place that it might not be continuous is where the denominator is 0. The denominator is going to be 0 at x equals 0 and also at x equals 1 because the natural log of 1 is 0. But we notice that our function is going to start at 2. So we really just care that this is continuous, positive, and decreasing when x is bigger than or equal to 2, because that's the starting point for our series, so it will be the starting point for our function as well. Okay, so we notice that 0 and 2, those are smaller, or 0 and 1 are smaller than 2, so we don't have to worry about this function not being continuous. So this function is indeed continuous for x greater than or equal to 2, which is all that we care about. Is this function positive? Okay, you might want to test this, but natural log of x is positive if x is bigger than 1. Okay, so because x is bigger than 2 in this case, the natural log piece will be positive. Also, x is positive if x is bigger than 0. So since we have two pieces that are being multiplied by each other, both pieces are positive. Since we're looking at x bigger than or equal to 2, then this whole thing will be positive. Okay, so that's good. On your paper, you probably want to write some of these words out. I'm going to be a little bit lazy today and not write them out. Okay, and then why is this function decreasing? Okay, we notice that all of the terms for this function are in the denominator, and natural log of x gets bigger as x gets bigger, natural log of x gets bigger as x gets bigger. X gets bigger as x gets bigger. And so the denominator is getting bigger. So x ln of x gets bigger. I don't know what I'm trying to spell there, guys. Um, gets bigger as x gets bigger. And so that means that if I look at 1 over x ln of x, that gets smaller as x gets bigger. And that tells us that f is decreasing. Okay. So sometimes there's a significant amount of work that goes into checking the conditions of the integral test, which is why we're not going to want to have to use it all that often. Another way that you might have to check to see if things are decreasing, especially if you have both a numerator and denominator, another way to check is to look at f prime of x and show that that is negative for the values of x that we're looking at. Because remember from last year, if the derivative is negative, then our original function is decreasing. Okay, so all we've done so far is check the conditions of the integral test. So all this tells us is that we can use the integral test. Okay. So you should keep all of this on your paper, but I'm going to erase it so that I have some space to work. So now what the integral test tells us to do is once we've checked that we can actually use the integral test, then we're going to look at the integral of our function. So we essentially just replace the summation symbol with an integral symbol and replace the ends with x's. So we're going to look at the integral from 2 to infinity, since the sum was from 2 to infinity, of 1 over x ln of x dx. Okay, now we have to integrate this. Oftentimes we're going to have to use u substitution just by the nature of these types of problems. In this particular case, we can pick u to be ln of x. So du is 1 over x, du over dx. So x du is dx. When we replace that, so if we look at, if I forget the bounds for a second, then we're going to have 1 over x times u du, so the x's cancel out. So we're left with the integral of 1 over u du, which will give us ln absolute value of u. And when we replace that, we'll get ln absolute value of ln of x. So we've got 2 ln's in there. Okay, so let's write that over here. And so remember, with an improper integral, we have to rewrite this with a limit. So we're going to get the limit as t approaches infinity of our answer, ln of x, and this has to be evaluated from 2 to t. Okay, there are so many things to do in this particular problem. Okay, so we've got to check our conditions. We have to do an integral. We have to remember how to deal with improper integrals. Okay, there's a lot. This is taking a lot of the ideas that we've done over the past 2 years and putting them all back together. So if you have questions, let me know. Now we're going to plug in our bounds. So we're going to get a limit as t approaches infinity, ln of t minus ln of 2. Okay, ln of t as t approaches infinity, that's going to approach infinity, and ln of that is also going to approach infinity. This is just going to be a number. So we're going to have infinity minus a number, which is going to give us infinity out. Okay, so now we have to interpret what that means. That means that the integral diverges. So, okay, so the integral diverges. And so by the integral test, if the integral diverged, then the series is going to diverge as well. So the integral diverges. So by the integral test, the series diverges also. Okay, so there was a lot there. Try this next example and see how far you can get. Stop here and then start listening to me again once you've tried it on your own. We'll try the integral test on this one again. What you should really do when you look at these problems is don't jump into the integral test first, because the integral test isn't the easiest thing to try first. If something else works, use it. But if we try the things from last time, if we started writing out the terms here, this is not going to be geometric. It's not harmonic. The test for divergence isn't going to work because the limit of the terms is 0. So we're stuck using the integral test here, but try the other things first, okay? So let's see. So we need to check, is this continuous? Okay, this one might have a little bit of a problem, so we might have to tweak this problem a bit, and this is probably because I just changed it. So when is the denominator going to be equal to 0 here? So if I have 2n plus 7 equal to 0, then, oh no, we're going to be good. This is going to be at n equals negative 7 halves. That's less than 1. So the only problem spot would have been if I was including negative n values here, but we don't have any problems. So this is continuous if n is greater than or equal to 1. Okay. And again, I should really replace these n's with x's. If x is greater than or equal to 1, x, because we're looking at the function 1 over 2x plus 7 squared. Okay, is it positive? This one's easy to see because we're squaring everything in the denominator. So since everything in the denominator is going to be squared and there's nothing that's not being squared, this is going to be positive everywhere. Even if I had a negative number in the denominator, it would get squared and then become positive. And is this decreasing? Yes, for the same reason that the last one was decreasing, everything is in the denominator. And the 2n plus 7 or 2x plus 7 squared gets bigger as x gets bigger. So this is good. Okay, so now we just have to compute our improper integral. Okay, we're going to have to do a u substitution again. So we can pick u to be 2x plus 7. So du over dx is 2. So du or dx will end up being du over 2. So my integral will be 1 over u squared times du over 2. And so I'll pull that 1/2 out front from the 2 here. We get u to the negative 2 du. When I anti-differentiate, I add 1. So I get u to the negative 1, and then I have to divide by negative 1. So I'm going to get a negative out front. So this is going to give me negative 1 over 2u. So 2 times 2x plus 7. Okay. So now I'm going to look at the limit as t approaches infinity. Negative 1 over 2 times 2x plus 7. We're going to evaluate that from 1 to t. We plug in t, so we get negative 1 over 2 times 2t plus 7 minus a negative, so that'll be a plus 1 over 2 times 2 times 1 plus 7. Okay, as t approaches infinity, so there still should be a limit out front here. Limit as t approaches infinity. As t approaches infinity, this piece will be 0, so that will go away. And we'll just be left with this piece here, which is going to be 1/18. Okay, so the integral converges. So by the integral test, the series will also converge. Okay, so integral converges. The integral converges to 1 over 18. The series, we don't know what it converges to. That's very important that the integral test does not tell us what the integrals or what the series converge to, just whether they converge or diverge. So integral converges, so by the integral test, the series also converges. And we don't know what it converges to. That's okay. We just care whether it converges or diverges at this point. Eventually, we'll learn how to approximate what it converges to, but we're not going to do that right now.